Welcome. This is the 11th of September, 2015, and this is episode 24 of the Unseen Podcast. This is your host, Paul Carr. I'd like to say a few things before we introduce our panel. First of all, this week's episode 23 was a big success, I feel, with a big international panel, including Laurent Planer and Jita Jaisinghani. And we talked about the problems with science and some of the possible solutions. Again, we're still looking for someone who can come on and tell us about their experience directly with publishing a paper and dealing with replication, reproducibility, negative results, that sort of thing. So if you're out there and listening, please give us a shout at unseenpodcast@gmail.com, and we'd love to talk to you and have you on the show, or maybe have you on the Wow Signal, which is our sister podcast. Another thing is, coming up soon, in early October, we will have some advocates of the Mars One program on the show. As you know, in a recent episode, we were very critical and skeptical of Mars One. These guys are very pro Mars One, and we'll have a chance to ask some questions. So if you have questions for those guys, please get them to us at unseenpodcast@gmail.com, or just go comment on the blog for that particular episode. Also, coming up soon on the Wow Signal, which we will have a well-known SETI scientist who will answer our questions about the recent breakthrough initiative funded by Yuri Milner, $100 million over 10 years. We'd like to know what you think about that, and also any questions you have. This is a SETI scientist from Berkeley, the University of California, Berkeley. Which is one of the few major educational institutions with a SETI program, and his name is Andrew Simeon. He was on the Wow Signal earlier talking about SETI at the square kilometer array. If you have any questions for him, I'd love to hear them. You can send them to wowsignalpodcast@gmail.com or unseenpodcast@gmail.com. As always, we want to hear from listeners, so please let us know what you think, how we can improve, who you'd like to see on the show, and so on. Now, tonight, episode 24, we have quite a pretty much the usual suspects. I'm looking at left to right of my Google Hangout on Air screen, and I see on the left Andrew Synergy Smith.
Adam.
I'm sorry, Adam. Adam Synergy Smith. Sorry, I just got stuck.
Hey, everyone.
Buck
Good to be
Field.
here again.
Say hello, Buck.
Hello, Buck.
No, say hello, comma, Buck.
Hello, comma, Buck.
I can't win that game. James Garrison.
It's really great to be here. And it's great.
Hello, everyone.
Patrick Festa.
Hello again, everyone.
Now, all these guys have been on many times before, so I don't think you need their bios again, but they are available. If you go to unseenpodcast.com, click on panelists, and you'll get a picture of their pretty faces, plus you'll get if you click on the picture, you'll get the bio.
Oh, shucks.
Well, everybody except Patrick is kind of average looking. All right, now tonight, here it is, 10:24 in the evening. So we're a little bit. If you're watching on Google Hangouts on air, I apologize we're so late, but we had to get the panel together. We had a couple of no-shows. Tonight we have a discussion of. We're going to start with something that I like quite a bit. I think it's quite an interesting topic, but has also been the subject of some pseudoscience, which is panspermia. Now, what is panspermia? Anybody want to kick that off? Define
Oh, I can.
panspermia?
Just in the layman's terms, it's basically where biological matter has gone from one planet to another planet. And as I've recently learned, there's actually 3 different forms of it. And if I get the names wrong, well, blame me from Oklahoma. Panspermia, which is when an impact causes biological material to go from one solar system to another. You have Ballistic Panspermia, which impact causes biological materia to go from one planet to another in the same solar system. So an example would be us getting struck by a comet and from the impact going to Mars. And then you also have directed panspermia, which is kind of the idea behind the last Aliens movie, where it's the intentional spreading of biological material by aliens.
Okay.
I'd like to elaborate on that. My idea of panspermia is not from one planet to another, but literally the impacts of the early solar system, the comets and etc. that brought us the water and things like that, also brought the biological material that caused whatever planet it's impacting to have the chemistry.
That's not really panspermia, though. That's just normal mixing of chemicals inside a.
I mean, the pan idea is that it came from outer space. That is, it came from the comets.
Well, no, the pan idea is that a living matter came.
Well,
from
that's
outer
true, but that's the spermia part.
Yeah.
The pan part, he's right about the pan part, but the spermia part is the replicating molecule part.
Mm.
Yeah, I mean, it has to be something that's already, in some sense, perhaps not in the sense that we would think of as in terms of modern Earth life, but is in some sense alive. That it can replicate, and once it has the right environment, it can also harvest free energy from that environment.
Well, it could just
The technical
be RNA.
Well, it could be DNA, but DNA by itself really kind of dies pretty fast. It gets torn apart.
I meant that RNA, that actually survives a little bit better.
Yeah, RNA does, but it,
And there's a hypothesis that there was RNA first.
Right.
Yes.
And then after it began replicating, then DNA formed, and then single cell eukaryotes and on from there.
Yeah, well, certainly something came before DNA. We don't know what it was. DNA is too complex to rise on its own.
I should have said hypothesis, not theory.
I think there's a body of evidence to suggest that the first living creatures on the Earth were replicating through RNA, and that DNA came afterwards. RNA is a lot more simpler chemical structure, and the first what they're called archaea reproduce through RNA, don't they? They don't have DNA. They have simple RNA strands, single strands of RNA, as opposed to double helix DNA.
By the way, I should point out Freeman Dyson wrote a really interesting book about this, where he excuse me, where he talked about whether replication or metabolism came first. And he
he's a big advocate of panspermia, isn't he, Freeman Dyson?
Yeah, to a certain extent. Not that he thinks that life couldn't arise spontaneously. I think, and that's something we need to understand better. And I think there have been strides in that direction in recent years. But we don't have, it's very difficult to find hard evidence for that because it happened billions of years ago and all the soft evidence is gone. So what we're left with is combination of our knowledge of chemistry and a little bit of knowledge of the early Earth. Now, one of the interesting things that I think...
We've got the residue. We've got the end products, and that's non-trivial.
That's true.
That's a non-trivial piece of evidence.
Well, we can certainly, when we know there was life, we have lots and lots of end products. But the very beginning, the end products would have been scarce.
See, this is where I have a problem with that. Apparently, I didn't have the right definition of panspermia, but see, I have a problem with that because when you start, to me, it sounds like pseudoscience, because when you start talking about the actual living organisms being brought here.
Well, I've talked to some very serious scientists who think it's not a crazy idea.
Then you have to wonder how they started, wherever they came from. So to me, the chemistry was here, and they have lots of scientific mountains of data about the beginning of life, RNA, DNA, and all that stuff, and it started.
Well, we don't, Patrick. We really don't have that much data about the beginning of life. We have a good knowledge of chemistry.
But the thing is that the chemistry was brought here by the impacts of the early solar system.
Maybe
I can't envision this living organisms being brought here after impacts, after the things would have been killed if there was anything living on these.
Well, now, Patrick, I'm sure you're well aware of the fallacy, the argument from incredulity.
No, I mean, in other words, I'm a strong believer in that the chemistry was brought here, but I have a very what's the word I'm looking for? My detector seems to be going off when it comes to actually bringing things that are already alive, smashing into the earth, and continuing to replicate after they came here. I have a problem.
They may not have been alive when they came here. It could have just been an RNA chain or even a DNA chain. They've recently found that with satellites, upon reentry, they're able to find bacteria that were sent up with them, or even the tardigrades. What's another name? Water bears. Those things are nearly indestructible.
Yeah.
So
I'll go with that. But I mean.
Yeah, but all it would take is a small piece of RNA to land on the primitive Earth with the proper chemistry, the old primordial soup theory.
Right.
You get
it's still basically it's the advanced chemistry, but it's still the chemistry.
Well, let's think about
the existing chemistry is here on Earth in terms of water. We have liquid water, and we're in the habitable zone. But the idea, the thing that got my attention was when you were saying that life came here, and what I would propose is that when it arrived here, it's not what we would consider life. It was just this molecule that, when it's in the right environment with liquid water and a certain type of nutrient available in the water, and the right amount of free energy from solar radiation and lots of other things, then this particular molecule, among all the billions and billions of molecular configurations that were raining down on the planet in the process that you talked about with accretion, perhaps very early, this one particular molecule happened to arrive in a suitable environment to where it could replicate and start the thing. But prior to that, it wouldn't have been life as we know it.
Well, I think something we have to consider is we know that early in the Earth's history, there were very heavy bombardments where the Earth's crust and the Earth's environment would have been at an extremely high temperature that would have destroyed almost any complex chemistry. So what we do know, the one data point we have that we can kind of count on, hang our hat on, is that almost as soon as Earth could have hosted life, it did.
Yeah, that's right.
Which means that either life arises spontaneously and very easily, which, is reasonable, or it came from somewhere else. And the somewhere else, there are two major suspects in that. One is Mars and one is Venus. We know that the environment of Venus early on was probably a lot more benign than it is now.
Well, I'm going to go with Buck's explanation. I like his explanation, but the idea to me of coming from Mars or coming from Venus, it's just a little far fetched. And then even if that's the case, again, you have to ask, well, if it came here by that idea, then you have to ask automatically. A scientist automatically asks, well, how did it get to that place that it got, on the comet or on the asteroid or whatever it is that brought it here in the first place? How did it get there? How did it start from there?
Well, other impacts knocked it off of the planet. That's easy.
Yeah, but how did it get to that planet? How did it get there?
How did it get there? It rose spontaneously there. Now the thing is that Mars may have been wetter and more hospitable for life early on in the solar system's.
I don't think
career.
He's debating that. I think he's talking about biogenesis, and that's the final question.
Well, I agree. But hear me out.
Cosmological question of where did the Big Bang come from?
No, not the Big Bang.
Well, no, but it's the biological equivalent of that cosmological question.
Well, all right. We're just talking about this little solar system, just this tiny corner of the galaxy that's mostly harmless. And,
yes, we're looking at our own solar system. Yes,
and
we're looking at our own solar system.
Well, the answer is 42.
I feel like I'll edit it down to harmless.
But what I'm trying to get at, Paul, is that you're talking about. Oh yeah, well, it started spontaneously on Mars or Venus. Well, if it started spontaneously there, why couldn't it start spontaneously here?
Well, it could have. I'm not. No, you're not following the logic. It could have started spontaneously here. That is not a hypothesis we can throw out, given what we know to date. But we also know that it happened very fast here. So, given the little bit we know about the early Mars environment, which is still very much a matter of scientific controversy, it could have been wetter and more benign earlier than the Earth environment. Life now, if you're asking what's the mechanism for life arising on Mars and getting over here, that's all been studied. It's all considered at least plausible, if not likely. And likewise, life has probably gone from Earth to Mars more than once.
Mm-hmm.
Yeah.
And also Earth to Venus more than once. So Venus may have Earth life, Mars may have Earth life, and it might have come from initially either planet. We don't know which, because we know that Venus early on in its existence probably had a much more benign environment than it has now. And Venus, of course, had more free energy than Earth. So, where would you if you were in charge of biogenesis, where would you start it? You probably started in Venus. Now, Venus eventually became a hellish place for life, but it wasn't always that way. That the atmosphere that it has now hasn't always had that. And when I talked to David Grinspoon about this, he thought it was plausible, not proven, certainly, but plausible, that life came from either Mars or Venus to Earth initially. Likewise, it might have gone from Earth to Venus or Mars. The chemical disequilibrium that they're seeing in the atmosphere of Venus may or may not be life, but if it is life, it may have come from Earth. So,
is there any general consensus on any of this?
No, because there isn't enough known about it.
I know I don't have any degrees or anything, but I'm going to go with what I've been thinking for the last several years, and that is this jumping between planets thing is a little far-fetched to me. I'm thinking more like it started on all three planets, essentially at the same time, give or take, years during the certain bombardment period, and the chemistry was brought to all the entire solar system was wrought with these chemicals, and it probably started on all three planets, if not other planets as well. Who knows? I think right now we're looking at the moons of Jupiter as well. But the point is, I find this jumping between planets thing is a little far fetched, and I'm thinking that it really started everywhere, and the chemistry came from the material that the solar system formed from.
Well, I think Patrick's voicing a very common perception amongst members of the public. They do have their doubts about the idea of panspermia. It's seen as a wacky idea, but it really isn't. There's a lot of good science behind it. Mm-hmm. I've seen some very good simulations, computer simulations recently, that show how easy it is for material to be shared amongst particularly the inner terrestrial planets. It's really not that far-fetched at all. There's a lot of, over the 4.5 billion year history of the solar system, a lot of material has gone from Mars to the Earth, from the Earth to Mars, Venus, and even as far out as Jupiter. It becomes more difficult for stuff to be thrown off the Earth and get out.
But nothing gets thrown off of Jupiter or Saturn. Gas giants don't do that.
No, but their moons do.
Their moons do.
Yes, they do. And
I think Enceladus is probably far enough out that if it has life, it was an independent genesis.
Yeah, but even so, even Enceladus could be reached by an impact hitting the Earth. It's unlikely, but it is possible. It's not statistically zero chance of it happening.
Well, if we get up there and we find life that looks somewhat like Earth life in terms of its basic biochemistry, then that would be a surprise, I think.
That would be
even more of a surprise than finding life at all.
We're not going to find that.
Why?
We're not going to find life on Enceladus.
We're not going to find life that looks anything like life on Earth.
Just leave Europa alone. That's mine.
Yeah, because they have those 10-armed octopus things on there that we want to stay away from.
Yeah, I think if
that was
if we do find life, if we find life elsewhere in the solar system, I think it will look very much like life on Earth.
You know, actually, I'm with Adam because part of my general, science enthusiast idea of this life being throughout the entire solar system by material means that if the chemistry is the same, life may actually be very similar. Even if for example, say we find life on Europa.
Well,
if it's just microbial, it may be very similar to the microbes here. If it's more than microbial, then it may be very similar.
But even if it came from here, given that there's different environmental pressures on the organisms, it may not look
evolved differently. Yeah.
It may not look anything like what we consider.
No, that thing is alien.
Well, if we find a completely different biochemistry, that's evidence that it didn't come from Earth.
If it has a triple helix or
we don't know what we'll find, but
can you define?
It's not built out of proteins. It's not. It doesn't use enzymes. It doesn't use hormones.
Silicon based.
Yeah. Well, it'll be probably carbon based, but.
Have you guys heard of the red rain phenomena?
Yeah, I heard of that
in India.
I'm not very persuaded that was much to that, but
what is it?
It's like algae bloom.
I mean, in 2001, in southern India, in the monsoon season, it started raining red stuff, and a lot of the southern Indians thought this was some sort of portent of doom, a sign from the gods or whatever.
Raining blood. Who would consider that as a bad omen?
There was a physicist called Godfrey Lewis, I believe his name is, who decided to look at this red stuff. Most the government scientists thought it was dust. He took it into his lab, he examined it under an electron microscope, and he discovered that this stuff was single-celled, what looked like blood cells, he said. except that this stuff had a very thick cell wall, which ordinary blood cells don't. And so we sent it off for DNA analysis, and there was no DNA. There was no trace of any DNA in
That's
this stuff
interesting.
at all.
Let me
Yet
see.
it looked like single-cell biological material.
It's a microalgae.
That's about as far as the study went.
It was a red microalgae.
Yeah, from what I remember, I vaguely remember the story, and I remember it being an algae.
Yeah, but it couldn't identify it with any existing form of algae on Earth, which hints at the possibility that it didn't come from Earth. But like I say, that's about as far as the study went. There was no conclusive evidence to suggest anything more.
That's interesting, because it could have been a meteorite that during the rain it seeded the cloud.
Could have been a lot of things. It's hard. You can't jump to conclusions when you get stuff like that. The Earth itself is full of many, many phenomena that surprise us. So,
oh, come on!
Yeah, the jury's out.
Jumping to conclusions.
Oh,
yeah,
aliens.
Yeah, it's aliens. Wait. Let me get my hair ready. It must be aliens. No.
No, yeah, your hair is not nowhere near there. You got to get.
Well, I mean, there's so much phenomenon that's so both beautiful and strange here on Earth that not everybody saw. For example, the luminescent waves in the ocean that only some people have seen. Lightning sprites that only some people have seen. When somebody like me or you sees these things for the first time, I'm 56 years old. I might go out there and I might see a sprite, or I might see the first time I see an aurora, for example, because I live in New Jersey. It's not likely for me to see them. These things are strange to me.
Yeah, green lightning. You ever seen green lightning?
That get the chance to see these odd things, and right away the imagination starts running away.
Yeah. And as we know, it's a logical fallacy to assign your favorite fantasy to the unknown, right?
Well, yeah, that's where my detector goes off. When I start, I thought panspermia was what I was saying, but you defined it as differently.
Well, I have to warn you that
going off because I'm thinking, well, all the planets were probably seeded in the same way.
There is, in my view, and if anybody else feels differently, speak up, but there has been a pseudoscientific aspect to panspermia, which the notion that life only comes from life keeps kicking the can down the road to where did life come from, and there, and then we get your creationism.
That's exactly the detector that's going off in my head.
I don't think that's really what we're talking about. We're talking about the fact that life could arise somewhere. We don't know how probable it is. It might be very low probability. But if it arises, it might spread by natural processes, not by... directed panspermia is pretty cool concept, but right now it's confined to science fiction. Hey, I'm open to anything if there's evidence for it, right? Now with panspermia, we don't have any direct evidence, but we have some indirect hints that there may be something to it. And there was a recent paper, I think we should probably bring that up now, by some credible scientists. This was not a joke. This was not pseudoscience. It was statistical signatures of panspermia and exoplanet surveys. Now, this is kind of a hypothesis paper by Henry W. Lin and Abraham Loeb. These guys are the real deal. They're not, and they developed a statistical model based on something that's sometimes called percolation theory. That shows how life might spread from star to star. Let me. I know this is an unscripted podcast, but let me just read the abstract. It's pretty short. Okay. A fundamental astrobiological question is whether life can be transported between extrasolar systems. We propose a new strategy to answer this question based on the principle that life which arose via spreading will exhibit more clustering than life which arose spontaneously. We developed simple statistical models of panspermia to illustrate observable consequences of these excess correlations. Future searches for biosignatures in the atmospheres of exoplanets could test these predictions. A smoking gun signature of panspermia would be the detection of large regions in the Milky Way where life saturates its environment interspersed with voids, where life is very uncommon. In a favorable scenario, detection of as few as about 25 biologically active exoplanets could yield a 5 sigma detection of panspermia. Detectability of position-space correlations is possible unless the time scale for life to become observable, once seeded, is longer than the time scale for stars to redistribute in the Milky Way. So, what they're saying there is that we can test, given some assumptions, the hypothesis that life could spread from star to star, not just from planet to planet, from star to star, given that the time scales are short enough.
First theory of panspermia.
Say again? Sorry?
That first theory of panspermia, the litho-panspermia.
Yeah, it would be bits of rock maybe blown out by a supernova, or just traveling between star systems, falls from one to the other.
Do bits of rock get blown out by supernova?
Well, sure, why not?
On the outer edge of the star system,
I mean, all the heavy metals and stuff like that we have here is because of a supernova, right? The iron in our blood, the nitrogen.
Right.
But I mean, supernovae are very short-lived stars. They don't really form planetary systems.
But do they form rocks?
Well, the rocks would already be there from just detritus floating around. The supernova might give them a lot of velocity they could use to move between stars, or it could be just a gravitational disturbance. These guys don't really model that. They just say,
okay,
the rocks could move around between stars.
They're talking about population monitoring. Is what they're talking about.
I normally think of rocks and stars as being in really different categories of matter.
No, they actually come from the same cloud.
Well, where they come from is immaterial. I'm talking about like states of matter. A star that is going nova, as far as I know, doesn't have anything in it that I would call a rock, because it's like...
That's true, but it has something called a shock wave, which will blow the hell out of anything.
And it has huge amounts of heat and light and stuff that is not rock-like. I mean, it's plasma.
I imagine it's a lot of...
Yeah, but if any of those bits is there...
I could also imagine chunks.
But if any of those bits are going through space and they strike another object, they could easily have the momentum and the mass to throw pieces across the solar system.
Yeah, I mean, that's the thing, is you get this expanding gas shell, and it hits small pieces of rock that fell off of planets, not from the star that was a supernova, because they are very short-lived. Typically, you're not going to get planets. Well, you can get planets, but they won't have developed life. But you get bits of rock, those could get accelerated to very high speeds and blown out all over the local area. Likewise, just simply a flyby of a large planet or another star could kick it out of the solar system. There's other mechanisms for knocking it out of the solar system. There's many, and they all, we're talking about a very low probability event, but we have lots of time.
Lots of time.
In the paper, in the paper we're talking about, they talk about two ways in which life can be spread. Firstly, gravitational slingshotting of asteroids or comets, basically. And the second way would be directed panspermia by an intelligent life form.
Right. Well, I think all bets are off if we're talking about the latter, right? I mean,
yeah, I want to steer away from the latter. Like if
because I think it's possible, but I just don't think that we know.
Are we not
anything about how
ourselves to do that? We have the technology to send microbes off into space if we choose to do so.
Yeah, well, we do so unintentionally all the time. In fact, there may be microbes on Voyager.
You know, I don't see why it should be that remote a possibility. If we have the ability to send off robotic spacecraft, which we may well choose to do to safeguard and preserve life on Earth, maybe we will at some time in the near future choose to seed nearby planetary systems with life. Why not?
Well,
yeah, I agree with that, but it's the more you talk about other civilizations doing that, the more you go into the realm of science fiction. Not that it's impossible, but then you get the pseudoscientists and the conspiracy theorists who want to grab onto that idea and turn it into something that is not science.
I'm not going to let what crackpots will do with ideas limit legitimate theorizing.
No, why should we? Anyway, Lin and
don't let crackpots or the terrorists or whatever determine what you're. Don't let the abusers determine what you do. Do what's right, and let time sort it out. I mean, we need to support good reasoning and good risk management, good thinking, and good philosophy of science and whatnot. But you're never going to be able to stop people from abusing anything.
Yeah,
want to abuse it, they're going to abuse it.
Oh, yeah. Well, quantum physics is the most abused thing on the planet. It's also the best theory we have of how.
No, the statistics say
behave.
I can't disagree with that. I can't disagree with that assessment. You know, but it is my. I guess we talked about this in another podcast. My bias. One of my biases is this idea that it just seems more plausible to me that multiple planets were seeded than it is, you know. But not that I think it's impossible. But the more I go into the other ideas, the more it starts to sound like science fiction to me. That's my way of thinking, anyway.
Other ideas as opposed to what?
I'm sorry, two people at the same time.
Other ideas as opposed to what?
In other words, when Paul and James were defining panspermia into different than I thought it was. What I thought it was more what I was thinking. I had this cringe factor. You know, I started to think, one planet to another. Okay, so where did it come from? You know, I started to think of the pseudoscience that I've been hearing, and it started to make me have that cringe factor.
I think that it's okay to cringe there because there is a creationist element that would like to assume that life didn't have a spontaneous origin anywhere.
Right. That's the problem with it. The
but
problem with
that's
it is
that's not an assumption of panspermia.
No, it's just explaining how life may have gone from one locale to another. Nowhere does it talk about the actual origin of that life.
You know, remember the abstract says if life arises spontaneously, independently everywhere, it should be spread out more or less evenly.
Yeah.
And if there's panspermia, it should cluster. Now, the paper does not say panspermia happen. Now, the mainstream media bless their little hearts, got this completely wrong.
They have hearts.
They said panspermia could happen from star to star. Says, and that's not what they said. They said if panspermia happens, it will look like this, and if it doesn't, it will look like this. And we ought to be able to tell statistically with enough data, once we have some exoplanet information, which is the next generation, 20, 30 years away, we should be able to tell the difference. That's all they're saying. And that's based upon their model of panspermia, by the way. So it's not the last word. It's just simply an opening salvo.
I agree with that. It's maybe because, I don't know if you guys know this, on my Hangouts and my Google life is basically cursing out creationists and stuff. And my bullshit detector goes off so many times with these people that when I sense these things and I know what they use, and like Paul, you just said about this is not what the paper said, but they will use it. They will twist it.
Are not proposing creationism.
Their job is to twist these things,
We all put things into the paradigm that we have to make sense of the world. I mean, the fact that we see things the way we do is based on the rods and cones in our retinas that enable us to see certain frequencies. If we saw different frequencies, we would see things differently. And people who are creationists have one of the things in this debate with Bill Nye and was it Ham?
And Ham.
Ham. Okay. Ham was better in terms of philosophy of science rigor. He was better than Bill Nye on foundations. He was better because he said, look, this is my foundational paradigm for interpreting the incoming data. And what he said was, it's Genesis in the Bible as he reads it in whatever version he has. Now, Bill Nye could not do the same thing.
Bill Nye basically, to me, in my brain, Bill Nye made a laughing stock of him, and as far as I'm concerned, that's all that Ken Ham ever is. But let's not digress.
Well, I think what Buck is trying to say is that Ken Ham is a pure foundationalist, and Bill Nye is not. Bill Nye is a coherentist, and
no, I'm not, I don't think I'm saying that. What I'm saying is that I think in this particular dimension, in terms of understanding one's framework, Ham was better than Nye. Nye advocates for science that is more reliable, but he doesn't understand how and why it's more reliable.
Well, not just that, but Ham's entire basis has not, it's changed minorly through different reprints. Science changes all the time. Ham's idea hasn't really changed in 2,000 years.
My name is Ken Ham. I don't understand, therefore God.
Well, I would say Ham's paradigm has changed in terms of new data has come in, and it has required adaptation. Just like there are astrologers out there who certainly astrology has gotten more complex as new things have
but
been
I don't think I want to use the word paradigm to describe pseudoscience. That's cargo cults.
I'm trying to be polite here, Buck.
Giving them credibility.
You're bringing up pseudoscience and creationism.
I mean, you got to go back and read Feynman's lecture on cargo cult science.
On what?
Cargo cult science. It's
and Feynman doesn't understand the similarities between how he frames incoming information and how the cargo cult.
I think he did.
Imitators.
Feynman read everything.
He said things like, and this is something that people put in their signatures. It was such a quotable pronouncement of his, and I'm a big fan of Feynman, but he didn't understand first principles. And what he did was he said, look, it doesn't matter how beautiful or effective your theory is. If it disagrees with experimentation and observation, it's wrong. Well, that's fine to say, but the fact is that theories involve an infinite number of factors, and disagreement with observation won't tell you which
an
of those
number of factors.
Sure.
Can you?
And this is called either the web of belief. It was an idea that was explained by a guy named Willard Van Ornum Quine, and he said, look, when we take something like the sun coming up in the morning, when we say, look, the sun comes up in the morning, we're referring to a lot of things like morning. Well, morning for us is something different than morning for somebody in Australia or in India. And when we say it comes up, what does that mean exactly? Well, if you're in a heliocentric model, that is a sun-centered model, then what you think is the sun coming up is an observational consequence of the Earth rotation, and we're observing. If you're in a geocentric model, it means something else. So all of the concepts that you use to interpret some data, like the sun coming up, you observe, your eyes see this movement of the sun. This is interpreted by your brain, and you have all these ideas about what the universe is, and you tend to see things in terms of what you understand reality to be. And each one of these things, like, well, what is the sun? You can think it's a god. You can think it's a hydrogen fusion star. You can think of it in lots of different ways. But each of those things, we are digressing. Each of those things relates to other concepts, and this, as they expand, it becomes a very large body of concepts that that has lots of components. And what Feynman didn't point out was, well, what part is wrong when the failure of when there was the debate between the geocentric and the heliocentric model. Is the Earth the center of the universe or the sun the center of the universe? When this was a debate, there were people who advocated for the old Earth-centered system, and they said, okay, you Copernicans who say that the Earth is whizzing around the sun have a problem. If you're right, and the stars out there are other suns, then this huge distance that the Earth would have to travel around the sun, the stars should appear to shift. There should be a change in parallax. Well, if you're right, we'll see a change in parallax. So they did the experiment, and they made very detailed measurements of the positions of the stars 6 months apart. When the Earth was, according to the heliocentrists, the Earth would be on opposite sides of the sun. And what they found was there was no change at all in the apparent position of the stars. This should have refuted the sun-centered system. The sun-centered system disagreed with observation, according to Feynman's rule. What did the heliocentrists do? They changed the goalposts, and they said, no, it's not because our theory is wrong. Our theory is really right. It's just that the stars are so far away that we can't detect it.
No, that's not moving the goalpost. That is not moving the goalpost. It's the same goalpost.
It is if you agree.
It's just
it is if you agree in advance that we would observe this.
No, it's not moving the goalpost.
It's not moving the goalpost. The goalposts are the same. It's just a question of how the interpretation of the observations. And if we now know that the heliocentrists were right.
Look, the stars are going to show parallax change, and then we do the experiment, and they don't show parallax change.
But they do show parallax change. I don't know where you're getting this from.
Well, they do now.
Because at the time, they said, yes, we will see parallax change. And then they didn't.
But that's normal. That's normal science. That's not moving the goalpost. That's figuring out why your
If
hypothesis
I
failed.
say the goalpost is parallax change in the stars, and then this experiment doesn't go my way, and I say, oh, no, the goalpost is no longer parallax change, it's something else, I've moved the goalposts.
No.
I can't agree to a criteria, and then when it doesn't go my way,
Yeah,
I
but
say,
I
no,
don't know
that's
if
not
you
the
said that or
criteria.
No, not if you don't take into account experimental error.
Yeah, I was gonna say
That-
there was something wrong with the experiment, but I don't know if they
That
actually
or
said those.
they
things.
Right,
had-
but how do you decide it's experimental error?
That or there was
I don't
other
know, I don't know.
observational data
Do
that
the
they
analysis. You figure out what distance it would have to be at in order to be below the noise floor. That is
They
normal.
didn't know.
That is normal science.
I don't know, but the subject matter has changed here.
Well, yes, it has, but I'm not
Yeah.
I'm not going to stop it right now. Let's keep going. What I want to understand is, the fact that we now have
Here's
the
the-
Hipparcos catalog.
Here's the official version on this. A guy
Official,
named
who's official?
Robert.
We don't have
Robert
official
S.
anything.
Robert S. Westman is the name of the author, and this is like the most authoritative yet book on the subject
Well,
of how, and it's really a lot more the way that science changes in paradigm change is a lot more complex than the kind of cartoon candy-coated version that we're taught, and which Feynman learned.
Kuhn wrote about the Copernican revolution as well.
Yes, it was one of his exemplars of
And
paradigm
it just
change.
the Ptolemaic model just collapsed under its own weight. It was every new observation made it more complex until it just became ridiculous. And also every new observation made the Copernican model look better.
Hey, Buck, right quick on you're saying it was the moving the goalpost fallacy.
Mm-hmm.
Moving the goalpost is if let's just go back to your heliocentric geocentric example.
Sure.
It would be if the heliocentrists had proved parallax, and then the geocentrists wanted more evidence.
No, it was when the geocentrists.
I'm saying that's the definition of moving the goalpost. The one side, once it has been proven, wants more and more evidence.
Well, it's only fallacious if you say that, okay, what we really meant was X, without taking into account experimental error, without taking into account reasonable parameters in the theory. And now, in this
No
point,
one imagined that the stars
there
would
was
be
no
that far
mature
away.
theory. It was proto-science.
Right. But how did they couldn't have known that it was proto-science? By our standards, yes, it's proto-science. But if we were at that time, how could we tell? That's the question.
Well, they couldn't. But
so don't you think that applies to us?
No, I don't. I mean, I think.
Why not?
Well, because we have normal science now in all those areas. And if there's going to be a paradigm shift, it's going to be because we find anomalies, not because we just didn't know what we were doing.
Science has matured, and these people, Copernicus and these other people.
We owe an awful lot to Tycho Brahe, who back a long time ago, I think 500 years ago, something like that, saw a supernova and said, wait, or a nova, I can't remember which one it was.
Mm-hmm.
I think it was a supernova. He said, wait, the heavens can't change. Oh, the heavens do change. And completely, not only revolutionized astronomy, revolutionized science. Whatever the ancient authorities said may not always be cast in concrete. It may be something new to learn. And that is, we owe a lot to those early astronomers, even though they didn't have a good theory of what they were looking at. Along came Kepler a little bit later and said, hey, here's a good theory. Doesn't explain everything we see, but explains a lot. And it quickly took over. and for good reason.
I agree with everything you say.
So, but the problem is that but this was now. It wasn't that much longer. Another 100 years, we had exquisite theories for all these planetary movements. Well, maybe 200 years, but when Gauss came along, it was pretty much all solved to a good enough order that it was clearly the right theory. It wasn't the final theory. There is no final theory, but the theory was not to be thrown out, but to be improved upon. And that, same thing with chemistry. In the 18th century, they threw out theories they had and started over with new theories. And it wasn't until the 20th century that we unified chemistry and physics.
If I may, I think maybe Buck is trying to say that, for example, the general public is like those people hundreds of years ago who really don't understand what science is about, and they're still playing that game.
Well, I agree that science is complicated and messy, and sometimes the paradigm shifts are difficult to reconstruct because there was a lot of going back and forth and disagreements and people who hated each other's guts and therefore would not agree no matter what. But it's a human enterprise. But it doesn't mean that we're way beyond our senses now. Way beyond. We can see, we're this close to detecting gravity waves, probably in the next year or so. Something that the human senses can't even hope to detect.
Yeah.
We see X-rays, we see gamma rays, we see ultraviolet, we see infrared, we see microwaves, not with our own senses, but with our instruments. And so, we're no longer limited that way. It's no longer a question of what your eyes or nose or mouth or ears perceive. It's just not a factor anymore.
We're also very close to being able to answer the fundamental question of, are we alone in the universe? Over the next, 20, 30 years, we'll be able to detect signatures of life.
I think that we can we're close to answering the question in a positive sense. No, we're not. But if the answer is negative, it doesn't mean we've gone through the whole search space.
No.
I mean, if I may use my own example, I don't want to diminish these other ancient peoples, Copernicus and before them, even though the science was not mature yet. These people were geniuses. I mean, was it Copernicus who created this clock that showed the movement of planets, even if it was wrong, or was that Ptolemy? The idea that they were able to do this takes genius to begin with.
Are you talking about Foucault's pendulum, or
no? Was it?
Which is a really cool novel by Umberto Eco, by the way.
There was this motion of the planets thing in the geocentric universe.
Yeah. As Buck has pointed out, initially the Copernican model didn't fit the data as well as the Ptolemaic model. It just didn't have enough free parameters.
Right. And yet, I'm not dissing on Ptolemy because his model was wrong. It took him a genius to be able to build this abstract work of art, literally, that actually showed this clockwork thing.
It was very clever, yes.
Yeah,
as was the Mayan calendar,
but it was wrong. It was wrong,
yeah.
and when Copernicus came along and said, I think I know why there's an anomaly in your thingamajig, because I think actually the sun is at the center. This is coming from a layman, a science enthusiast myself. So I don't want to take away from these people's genius.
Well, the real genius is being able to spot the better theory that the idea fit the data as well as the current theory does.
The idea was that they were able to think about this and say, wait a minute, let's figure out why this is not working quite right. There's something wrong with this. And he was able to come up with a better idea. That's the birth of real science. To question another person's model.
the problem they were having was that every time a new planetary observation came out, the Ptolemaic system had to get more complicated, and it was
epicycles.
Yeah.
I don't think that's. I think that's the popular version, but I don't think that's actually true. I think that there was no problem with a geocentric model incorporating all sorts of new ideas. My read on the history is that it was a problem of calculation, not a problem of accurately modeling the cosmos.
No, that's what I meant. You can still model it, but you have to, your calculations get crazy. And whereas with the Copernican model, you have a paradigm that leads you to.
Do you know where Nicholas Copernicus got his money, or Nicholas Copernic?
No, where?
He got it from the Pope, and he was set up in Fromborg he was a priest. Copernic was a priest. And he got his funding because there was a crisis in society because they couldn't figure out what day Easter was. Easter falls on the first Sunday after the first full moon after the spring equinox. And the date of Easter was critical because the prayers that you said on different days could affect your chances of salvation. You had to pray to the right saint on the right day. Yeah. So they needed to find out what day it was. And the calendar they were using at the time was several days out of sync with the actual, and they had all these people working on it with the epicycles and the geocentric model, and the calculations involved were non-trivial. They were trying to solve this, and so this priest who had done a lot of astronomical study, he was kind of a rogue, but he had this reputation for smarts, and so the Pope said, "Okay, look, I'm going to give you a place to work. You're going to be able to have enough money to build all the instruments you need. You figure out what day it is. I want an authoritative answer and do whatever it takes to solve this problem. We're going to get our calendar straightened out." And that's how he came up with this model. And the part about the sun being the center of the universe, as they understood it at the time, that was only allowed to be published after his death, where he actually said these things. And then in the introduction, the guy who was actually releasing this for publication wrote in the introduction, "Well, look, we're not saying this is really the way anything is. This is just a mathematical convenience for calculation, and it has nothing to do with anything other than calculating lines and circles up in the sky that's convenient for us here on Earth and is part of all of God's plan. And oh, by the way, if you use this, it will help you solve the calendar problem." So it's a lot more complex situation. And one of the things that actually was a motivation for Copernicus was to generate greater support for astrology. The idea that with more precise calculations of celestial positions, we would be able to better predict what was going to happen on Earth. This was a big thing that personally he was trying to do and make astrology more reliable. You don't ever hear about that.
But can you connect that back to the question of why there was a shift?
The shift happened over a very long period of time and was really kind of, we call it the Copernican revolution, but it really didn't complete until after Kepler and the work that he did on planetary orbits and ellipses. I mean, this thing we think of it as the religious conservatives opposing this new science that was empiricist and observation based, but it was a lot more complex than that. And I think that in the kind of cartoon version that scientists are taught and people are taught in, Tyson does this in his Cosmos series. He teaches this kind of cartoon version where there's the old superstitious fuddy-duddies on one side, and then there's the new scientists. And Patrick, you were referring to, they didn't have mature science. And to me, this is a very dangerous view to have, that there were these old people these old ancients who didn't have the kind of knowledge and tools that we have today, which is sort of true. But in a certain standpoint, we have the same cognitive blind spots that just come from rational inquiry. To have a strong framework for analysis.
Well, I want to point out that the people who were, like you said, it's a little dangerous, but the Copernicans and the Ptolemies and the Galileos, these were the people that were ostracized for their actual extreme ability, thinking skills. And again, they didn't have the tools and everything, yes, but they were the ones that's why we know about them. That's why we talk about them after centuries gone by, because these were the geniuses. So that's why I said I don't want to take away from their genius. Even if they didn't have the obvious knowledge that we have today, they built it. And maybe science was born from their genius. But in fact, they were the ones that were ostracized from the Catholic Church. While they may have received their funding from there,
Galileo was.
When they found their answers, when they decided that, you know what, I think this is why we're having a problem with this Pope, because of this. All of a sudden, we're like, what do you mean? I'm being a layman at this, but in other words, these people were geniuses, no doubt. But when they used their thinking skills to discover something new, they were ostracized for it.
I don't know.
No, Galileo was.
Yeah, Galileo was. Kepler pretty much. I think he did better because he was later.
And I think
he died in 1630 something.
Yeah. Brahe was made rich by his work.
Mm-hmm.
Yeah, but he had to spend his time on the island of Vane.
Yes.
I mean, Denmark and whoever practically had wars over who was going to have to take it.
Yeah, that's true. But look at Isaac Newton. Isaac Newton was extremely well respected. He wasn't ostracized at all. No.
Well, can you really praise a guy who considered his major life achievement his virginity?
Well, no, but I think you can praise Newton.
Yeah, I mean, come on, like Neil deGrasse Tyson said, here's a guy that one of his colleagues or one of his friends asked him, can you explain this retrograde thing? And like, well, I'll let you know. He came back from vacation. He says, yeah, I figured it out for you, but I had to invent calculus to do it. And he was only 27 years old.
Maybe it was Asperger's syndrome, but
yeah,
that's
fine.
What
was I doing at 20-something years old? I was still a kid. I was still smoking weed,
Yeah.
As opposed to
being a brilliant scientist.
Well, Newton had a very brief period of incredible creativity, and then he kind of just
went off the deep end.
Started smoking weed, I think.
He did some weird stuff.
Smoking theology.
Isaac Newton created calculus in order to figure out a problem. and he did this in his 20s.
He and Leibniz created calculus about the same time. Yeah.
Well, my main thrust here is that I think we are well advised to understand that we are in the same position as everyone in the past who thought they had the best model of reality and the most accurate representation of all the observations available, because we think that now, and everybody in the past thought the same thing. And in 200 years, people are likely to look at us the same way.
Okay,
that
Buck,
we
I'm going to
look
ask you
at
to tie that
others.
back into panspermia somehow.
Yeah,
Be creative.
because we're questioning it. Because I'm questioning it. I'm disagreeing and I'm agreeing partly, and I'm disagreeing with Paul, and Paul's, this is what we're doing. We're actually civilly disagreeing with each other.
Well, there is literature that supports the notion that things like very small biological organisms, bacteria or something like that, can make the trip between planets.
And I agree with that, but I think it's very important for us to always keep in mind that our notion of, as we talk about things like life or replication or habitable environments, we make sure that each of those terms that we use, we understand that could be redefined. At some point we could say, well, you know what, life, it could be just these components that, if they come together in the right way, could replicate. And is a virus alive or not?
No.
Right.
A virus,
Right, I agree.
virus evolves after life. Other life evolves. It can't be the original life.
Well, yeah, but the point we're discussing it, and
well, then the question I would say is, how do you define a virus? How do you say, is this thing definitely a virus, or is this thing that is a molecule very virus-like not a virus?
Well, a virus has very. I mean, there's a whole field of virology, right? This is not something that we have to do soul searching over.
Well, this is what they said about the
virus
motion of the sun.
is a packet of DNA that uses other organisms to replicate itself.
I don't think viruses have DNA.
I know, but
they do. They definitely do.
They do.
Specific, Buck. You're being very specific, and this was a general, This was a general discussion. That's what I'm saying. In other words, we're discussing the ideas of panspermia, and my idea was a bit different, and I thought that it was a little bit far fetched, and Paul said no, and Buck said the other thing, and James said another thing. In other words, we're discussing the possibilities and who thinks it's more far-fetched. We're not arguing over it. We're not saying blasphemy. How dare you say that? We're not doing that they did centuries ago.
Well, in this case, I mean, we just came up with something where, I would say is where I'm sort of disagreeing with Paul, and I'm saying, well, I'm not sure that like a single strand virus qualifies as DNA, because to me DNA is a double helix. So
they have DNA.
Yeah, a lot of viruses, some viruses are RNA and a lot of them are DNA. Basically,
yeah.
Okay, but if it's a single
HIV
strand,
has DNA which it uses.
It's a replicating machine.
It has to be something that's replicatable.
A replicating machine is not the definition of DNA. My understanding of DNA is it's a double helix. Do we agree on that?
No,
yes, they do.
That's just the shape of the molecule.
Yeah, well, they do have DNA.
They do. There are some that are RNA. There are RNA viruses. They exist. Mm-hmm. There's several groups of them that have been defined. I think the probably the most common ones are the virus that causes colds is an RNA virus.
Rhinovirus.
Yeah. But HIV has DNA, for example. Basically, viruses are hackers of life.
Okay, but you have to agree that that's a pretty amorphous definition.
Okay,
yeah, it is.
What does this have
it's meant to be a metaphor, not a definition.
Yeah, I mean, I don't know enough, and I'm going to take Paul's word for it. It sounds like he's informative. The point, Buck, is that how do you feel? How does that coincide with panspermia?
Well, it goes back to the idea of where you were saying life being conveyed to Earth. And to me, that when you have to define, well, what is life? Is it a replicating thing? Well, if it's in space and it's frozen, it's non-replicating. So that would mean it's not life, according to that definition.
No, it doesn't have to replicate right now. It has to be able to replicate.
Okay, well, I would say under the right conditions, you could probably get anything to replicate, which we wouldn't want to call life.
No, you can't get anything to replicate.
Like what? What can you
get
not
water
get
to replicate?
Okay, well, I would say that if you get a bunch of water and have it in a star where it creates more water, then
it's not replicating. That's not replication.
Why not?
Replication is an active process of making more copies of yourself.
Okay. Well, and then we get into like the other definitions. The point being that our language is
there's not going to be any
dubious.
water. There is the hydrogen and there's the oxygen that was created by the fusion, and later on they combined into a molecule called H2O. But you're not going to find water in a star. You're going to find the hydrogen. You may actually find
you can find water in some stars, but it's very highly ionized.
Yeah, and so the star process would be an intermediate step.
Well, it's not really where that water comes from, but I mean, they're not created in stars. They can fall into a star, but I think it's much more likely to be created in a molecular cloud, where you just have.
I agree.
It has to be formed.
You need a cold temperature to make it happen.
And I agree, but the point I'm getting at is that what we're doing is we're setting these categories, and we're saying, well, here is a star, and here is a replicating thing that is a thing that we call life, that has a process where there's a molecule that undergoes a process, and then there's two of them. We call that process life, and then there's a process where, like water molecules, let's say from a nebula or something, collapse into a star, and the star undergoes a process, and it results in more water molecules. We do not call that process life. And all I'm trying to do is say, well, look, as long as we consciously decide we're not going to call one life and we are going to call another one life, and we're clear about our criteria, I'm fine with that. It's when we don't have the clear criteria that I say our terms are vague enough to introduce risk to our theory.
Well, and so far we only have one example of life. So
that's important.
It's hard to create a general definition from that.
Well, let me give you my layman's science enthusiast definition of life. Okay, to me, a virus is alive. Okay,
it is.
As far as I'm concerned, being the layman I am, as far as I'm concerned, it's alive. Okay, self-replicating.
No, it's not self-replicating. It requires the machinery of other organisms to replicate itself,
or it invades other life to try to replicate it, or to me it's alive. It's either self-replicating or is a symbiotic type of.
It's not symbiotic.
It's parasitic.
Parasitic.
Could be symbiotic though.
Okay, symbiotic, parasitic, or self-replicating. As far as I'm concerned, it's alive. I think this panspermia thing has gotten to the point where I hate to say this, Buck, but you're doing what some of the religious people do. They
I get that a lot.
Talk about moving the goalposts. You're going off on tangents. So you're going off on like specifying. The hell with the specifications. You know, we're generally talking about life in general, you know, microorganisms, you know, and that could be viruses, you know, if you want to say that viruses are not alive, fine, you know, but that's really what we're talking about. To have this podcast over argument about what a virus is, whether or not it's alive or not, is to me a little off the subject.
Well, I'm trying to get at clarity. as long as we can, what I want to do is I want to say, well, look, if we're going to talk about life or we're going to talk about anything, then it's most productive if we have a really clear understanding of what it is.
Well, yeah, I think the best definition we have, and I'm putting this in very simple terms, is self-organizing chemistry, self-organizing, self-replicating chemistry that can harvest free energy from its environment.
And with a capacity to grow and die.
Well, death is not a requirement. Growth.
It is
not a requirement. Oh, wait a minute.
Self-replicate. I mean, single cell organisms don't grow. They just.
Because it's a Medusa jellyfish that's able to regenerate itself completely.
Yeah.
And I hate to be the devil's advocate, but to say it's self-replicating with the ability, I mean, nothing's inherently self-replicating. It requires an environment where there's matter and energy. So
yeah, it has to harvest free energy from its environment. And what environment it needs for raw materials is TBD. But it doesn't mean it can't be dormant for a very long time.
So, for example, like water molecules in a nebular cloud.
No, they don't self-replicate. They don't harvest free energy.
Okay. How do you know?
How do I know? I think we know everything there is to know about water.
Well, okay. In the example of a nebular cloud that collapses into a star and ends up producing more water molecules at the end of a very long process. It doesn't produce more water molecules.
Not at all.
The fact that we found water in the nebulous cloud is a beautiful thing. Water is for life as we know it. Life as we know it, I'll repeat that, is essential for life as we know it. So water being on this planet, whether it was brought here or not, is part of the chemistry that was able to.
There's been some exciting work.
You've got H2O molecules.
Yeah.
H2O molecules
water
in
itself,
the cloud. They collapse into a star.
Buck, the water itself is not alive.
Well,
period.
But listen.
Water facilitates life, but water itself is not alive.
I agree. But what I'm saying is that the definition of something that is replicating, I'm saying, look, if you want to say a virus or DNA is alive, but an H2O molecule is not,
that's
then
easy. That is dead easy.
Okay, tell me the difference.
How about actively trying to replicate itself?
Well,
okay, what do you mean by active?
Self-replicating means that it has the machinery it needs to make a copy of itself, right? But water does not meet that definition.
Nothing has that.
Yes, it does. Every cell in your body has that.
It all depends on the environment. No, it depends on the environment. If I were out in a vacuum,
well, of course it depends on the environment. Why is that interesting?
Because I'm saying that the environment around water molecules allows for the production of more water.
No, water molecules are ordinary chemistry. They are not self-replication.
They're not seeking to increase their number.
Why?
Why?
Well, what does seeking mean? What do you mean by seeking?
They don't hunt for mates.
A DNA molecule doesn't.
Well, no, a DNA molecule creates a phenotype that hunts for mates, right? Through a very complex process of development.
And just a single strand of DNA, I don't think has ever been considered actually as a life form.
No, it's not. You need.
Yeah, I'd agree with that.
The machinery around it. You need the enzymes. We're used to. If you look at the, we can. I don't want to turn this into a biology lecture because I'm really not qualified, but. I'm
arguing for caution in our language.
No, I think that's just saying anything can be anything, which is not interesting at all.
No, I'm saying the opposite of that. I'm saying we should be cautious, much more cautious than we're being.
Buck, I'm sorry. I have to agree with Paul. Yeah, I'm trying to be as polite as I can, but you're going off on a kind of a ridiculous tangent.
Okay,
here.
but let's talk.
Okay.
Can we get back onto the paper? that kicked this whole thing off. The paper by Loeb and his colleague, who I'm trying to remember,
Henry Lin.
Yeah, Henry Lin. Thank you.
Mm-hmm.
What they did was create a statistical model of panspermia, which I think, from my quick skim of it, sounds like a really nice contribution to the state of the art. And they didn't really dig deep into the mechanism for panspermia. They said this is life, and once life hits a habitable environment, whatever that is, it should affect the atmosphere of the planet, and in a way that ultimately we should be able to detect maybe not even the next generation telescopes, but the next generation after that. And so we're probably 30, 40 years away from having the right instruments to detect it. So what they are doing is putting out there this, say, how can we, let's have this conversation about how we can detect panspermia versus spontaneous origin of life. Let's model that. And here's our proffered model, and it's a challenge to the rest of the community to come up with a better model.
So is that similar to like the Fermi paradox, talking about other intelligence expanding out?
It is kind of similar to that, in actually in interesting ways. The work the very simple concept that Jeffrey Landis had back in 1990 or even earlier was that we can model the expansion of civilizations in a way that's similar to the modeling of the expansion of life, which is similar to something called percolation theory or random graph theory, which random graph theory happens to have a very well-developed theory. Now, this is an approximate model. Nobody's claiming that it's an exact model of exactly how life starts on planet X and propagates to planets A, B, and C. That would require tons more data than we could ever have at this point. But what they do say, what Landis said is, look, we already know from percolation theory that there's a critical probability. You hit that probability and everything blows up. Below that probability, things are quiet. I hugely oversimplified that, but that's the basic idea.
Well, yeah, it's like any other hypothesis. You have an idea, you make an observation, you say, well, let's see how we can test this. That's what science is about.
Yeah, that's what science does, is basically create models of things. The models are sometimes very simple, sometimes very complex, depending on the maturity of the model. I don't know if you ever tried to do a calculation in atomic physics, but as soon as you get beyond hydrogen, it gets really hard. But people do it. People do it for a living. And the fact is that they're now getting to where they're very good at modeling simple molecules, and they can model complex molecules more approximately, but still pretty well compared to what they used to be able to do. Those models are they're very hard to execute, but as our computing power has grown, we've gotten better and better. Same thing for our model of gravity, right? The folks at JPL model the planets, motion of the planets, asteroids, comets exquisitely well using good old Isaac Newton's theory, with maybe some very tiny relativistic corrections, which are so small that they're almost unobservable. And they put out their ephemeris tapes all the time. They have we know where Jupiter's going to be 300 years from now to exquisite accuracy.
Right. Well, when it comes to looking for life, it's like you said, you have a model. So we come up with 2 or 3, maybe even 4 or 5 models, and we're talking about panspermia. The next step is to start collecting the data. The problem is that we don't have quite the equipment to do it yet. We're starting to talk about it. They're starting to talk about being able to look through the atmospheres of exoplanets to see if they can detect the certain molecules and things of this nature. This is the data collection that needs to take place.
Right. Well, that's exactly that's the right step, though. Form the hypothesis, then go collect the data.
Yeah.
And what we will find will probably be surprising, and will result in new hypotheses that are completely different.
Right. We might find something. Oh, wow, we were wrong. Who knows? But the point is that we need to
being wrong
collect the data
is perfectly all right.
Right.
Being wrong is actually the only way to proceed that I know of.
Right.
You got to be wrong lots of times before you get it right.
But we're at the verge of collecting that kind of data. In other words, the James Webb Space Telescope is going to go up, and they're going to start trying to determine the atmospheres and things of this nature. This is the data that we need to collect that we haven't been able to collect.
James Webb is only going to be able to do that to a very limited extent.
Right.
It's a narrow field, isn't it?
Astronomers are very clever people, though. They will find ways to do it better than I think. But
right. Well, the point I'm trying to make is that we're on the verge of collecting that sort of data that we need to find the data for that hypothesis to either be confirmed or denied or but we're on the verge. We're on the edge.
Yeah, I think. But what
it occurs to me that there is a big problem with the hypothesis. What they're saying is that life, if panspermia is correct, life will cluster. So you'll get oases of life distributed in little pockets around the galaxy. Yeah. The big problem is that stars don't stay in the same place. They drift throughout the Milky Way, so that the neighbors that we have now around the local solar neighborhood will not be the same ones that we had a few million years ago.
They state that in the abstract,
or a few million years into the future.
Yeah, you look at the last sentence in the abstract.
So those clusters, if they did exist when life arose on Earth 3.5 billion years ago, say, will have distributed themselves way out, across the spiral arm.
Yeah, and they acknowledge that. They acknowledge that. I mean, they say if there's effectively a mixing time whereby the pattern is lost because you've done too much mixing, right?
Exactly.
And so if that mixing time is significantly shorter than the panspermia time, the distribution time, then you'll never see it.
I don't think we will. I agree with the hypothesis. I like the idea, but I think it's too late. It's going to be too late for us to detect planets close to Earth that life may have arisen on, because they're going to be dotted around the galaxy.
I think that would be great if we detected so much distributed life signatures in the atmospheres and whatnot that it just looked like the panspermia theory was refuted, or whatever. I would just love to see lots of life occurring, a lot of life signatures.
It's not that panspermia would be refuted, it's just that we wouldn't be able to prove the hypothesis.
Well, the idea is
it wouldn't
that
be observable.
We have to try, and once the idea was set forth, once the question was asked, once the hypothesis was made, the quest for the information needs to be done.
Well, the Lin and Loeb paper, like I said, is just the opening salvo. It's this is I think it'll be 30 or more years before we have a telescope that can test this hypothesis. It might be 40 years.
I think more solid evidence is likely to come from a finding
in a line of in a long line of better ones.
Yeah. We're more likely to get better evidence from finding life elsewhere in the solar system. If we can find life on Europa, Enceladus, any of the 9 bodies, I think it now is, that have subsurface oceans, then that's a big pillar to support panspermia.
Yeah, I agree.
And
Well, panspermia
So I
within
would
a
say
solar system is not the same thing as panspermia from star
no,
to
it's
star.
not. No,
I mean, going
no,
back
it's
to
not.
these guys' paper too, if we do by chance find signs of life on another planet, we have computer models and powerful enough computers that we can show positions of the stars they were, 3 billion years ago, and see if that falls within their hypothesis too.
Mm-hmm.
If that does, then we can also take the old models versus the new ones and kind of track out and give us a better idea where to pinpoint other searches.
That's true. We might be able to unmix the galaxy a little bit.
Yeah, that's the beauty of the ancient Chinese astrologers. Excuse my blasphemy, but they even though they weren't doing actual science, they were actually very good at charting the skies. And we can refer back at least a couple thousand years or so to give us.
Well, we don't even need that. I mean, I think we understand, the nearby stars, how they're moving. Question of, and we can model it dynamically to some extent.
It occurs. Sorry, Paul. It occurs to me that a good test of panspermia might be to go and explore some of the so-called hot Kuiper belt objects. There are two distinct populations in the Kuiper belt. There are the cold classical Kuiper belt objects that have a low eccentricity, like Pluto, and there are the hot Kuiper belt objects that are very eccentric. Sedna is the prime example, and there's a whole family of so-called Sednitos that may just have been captured by the sun, the gravitational pull of the sun. Their orbits, their extremely eccentric orbits, tends to suggest that they've been captured by neighboring star systems, that the sun captured them from neighboring star systems. If we were to find life on those, or organic material on those, that would be a big plus for panspermia.
Yeah, I think it goes back to the beginning of when panspermia was being thought of. The idea was back when I was still in high school, was if we can find any even microbes on Mars, the life would be a lot more prolific in the universe in general. In other words, the question of where are we alone?
Well, unless they came from Earth, right?
Well, what I mean to say is that even if they found a microbe on Mars, the whole Mars exploration thing back from 1970s. I graduated in 1977. The whole idea was if we could find any kind of life, any microbe, anything, anywhere in this solar system, it would mean simply that life is more prolific, throughout than we imagined.
Well, what if it came from Earth?
Yeah, unless we put it there.
Yeah, or if Curiosity carried it over there. I
mean, there are safeguards. Generally speaking, let's not pull a buck. Let's not go off on tangents here.
No, I think that's a fair question, don't you? If we didn't have a separate biogenesis, then
we could find separate, alien life. Whether it be microbiology or heaven forbid, we find actual animals on Europa swimming around. The point is that we could find any life of any kind in our solar system other than here. The idea was, at the time, that would mean that life is a lot more prolific than we imagined.
I mean, you figure that we've habitated a whole nother planet with nothing but robots. They could have carried bacteria to Mars, and we could be the progenitors of panspermia on Mars.
Yes, but we do check for that. But go with me here on this idea of let's put that idea. We know that does happen, and we know that there is a probability of that, and they do check for that. The idea is if there was a perfect experiment to find microbiology on another planet, Mars. That's why they sent up Phoenix and they sent up the other rovers before Curiosity.
There's some tentative evidence of microbial life on Mars. There's a geobiologist called Nora Nofka who looked at some of the images from the Curiosity rover, and she looked at an area called Gillespie Lake, which is in the Yellowknife Bay area of Gale Crater, and she said that the rock structures in Gillespie Lake look just like fossilized microbial mats that you get on Earth. It's a very tentative conclusion, but I mean, she's an expert in her field. She's an expert in microbial mats.
Yes,
yeah.
I heard about that, and I actually saw a documentary on that. That was very interesting. But you know what? As a layman that I am, and a science enthusiast that I am, it was enough. It was enough for me to see Curiosity land at the base or in the middle of a delta, an alluvial fan. The fact that the fact is that I have, as far as I'm concerned, absolute evidence. There's no controversy in my mind that Mars was in fact once a wet planet, and the old adage about where you find water you find life. As far as I'm concerned, it was there. We just haven't found it yet, because I know that Mars was wet, and I know that in fact there's actually deltas and all kinds of moving water. A couple billion years ago, it was there. And
is there any controversy about these weeping vertical walls that turn
they have
dark
dry
when
lake
the sun...
beds. They compared it to the
No,
ones
I'm
that are in
talking
the
about
desert.
wet.
They have dry. I mean,
this
place was wet. This place had flowing rivers. This place had bodies of water.
Okay, what about now
rivers.
though?
You mean
the
gullies that have been
There's
observed?
definite geological evidence. There's definite geological proof that this place was wet at one time. As far as I'm concerned, being the layman that I am, as far as I'm concerned, where there was water, there was once life. As far as
I went to a conference, American Institute of Aeronautics and Astronautics, and they were giving somebody who was up on the latest Curiosity mission. They were talking
about recurring slopes linear. Yeah.
Yes. Yeah. And they think that this is water, and they were saying that we want to get over there and we want to take a sample of this. And I'll never forget this guy's presentation because it gave me shivers. He said, "We want to get a sample of that because this looks like it could be water, and there's no place on the planet Earth where you can go and scoop up a sample of water and it is not full of life. And what we need to do is we need to go over to that area that looks like the liquid water, and we need to scoop that up and sample it."
Well,
yeah, I actually have a picture. I actually have a picture on my computer. They actually saw a wet spot. Curiosity took a picture of a wet spot.
Okay. Don't all of us think that there's a better than average chance that that's got living stuff in it?
I certainly do.
Nobody knows. I mean, Mars certainly doesn't behave like a planet that's got a lot of life. But
no.
I got to believe that if there's liquid water there, there's some crap living in it.
Well,
here's the story about that. The thing is that it was liquid because it had metals in it, salts or some sort of salts. Not table salt, but metals. And even though the temperatures were below freezing as we know them, the salts caused, when the sun was shining, caused it to defrost, and actually the soil was actually wet. But you're right. As far as I'm concerned, I completely 110% agree with you. We need to.
We know that there's water on every body in the solar system, with the exception of Venus. Well, there's evidence that Venus had water long ago, billions of years ago in its past. There are, I think it's 9 bodies in the solar system now believed to have a subsurface ocean. So, if you think there's there's life on Mars simply because there's water there. Then there's Mars on Ceres. There's Mars on life on Pluto. You know, there could be life on all of the Galilean moons.
Well,
life could be everywhere in the
truth
system.
is, we simply don't know. But
no, we don't.
We don't know.
But it's not a bad hypothesis to go and sample that stuff and see what's there. The only question is priorities, right? I mean, that would cost a lot of money.
It would be extremely salty water on Mars.
Yes, it would. Salty and probably acidic.
Yeah. Well, I mean, we have extremophiles on Earth that live in those conditions.
Yeah.
I think we talked about this in another podcast. The ability for our detectors and our robots to actually detect actual quote unquote life is limited, and that's why there is this push to send people there.
This is a topic for another podcast, but we did talk about Gilbert Levin someday, and his experiment, which flew in the Viking lander. But let's hold that off for now. I'm actually hoping to get Dr. Levin on the WOW signal. He's still convinced that Viking detected life. So he may even thinks that the Spirit rover may have seen a microbial mat, as Noronofsky thinks that Curiosity may have seen a fossil microbial mat. And by the way, I interviewed Dr. Nofsky last year on the WOW signal. I'll put a link to that in the show notes. Folks, I think we're going to wrap up here. We've been going for about 100 minutes. So I'm going to give each of you one last chance to say something to close out the show. And don't worry, it's not the last. Nobody needs the last word. We'll have a chance to talk about it again. So let's start with Adam.
Well, there is no compelling evidence to suggest that terrestrial life originated here on Earth. It might have done, but there is no evidence. We can't exclude the possibility that life came here from elsewhere. It may have been that this planet was seeded by an advanced galactic civilization. Some people think that's a ridiculous idea, but it is a distinct possibility. It is. We don't know. And until such time as we do know, we have to keep an open mind. I'll leave it at that.
Okay. Buck.
Always a pleasure and interesting as always. I would say that regarding the question of the spread of life, it's I would urge for caution in the confidence that we have and some skepticism and willingness to accept that our definitions of life and how it is composed and what it is defined as are subject to change, as all scientific concepts are supposed to be.
Okay, James.
This topic got a lot bigger than I'd intended when I suggested it, but it's been pretty interesting. And
that's what my mom said about me.
I'm not going there, but anyway, no, it's been a lot of fun, and I think this would definitely be something to come back and check. Come back and talk about it later.
Yeah, we will. And we need to follow up on Dr. Nofsky, and we need to follow up on Gilbert Levin. Patrick Festa.
Yeah, this has definitely been an educational hangout for me. It is continuously have been my idea in my own mind that life is likely to be throughout the galaxy, and life has been seeded throughout any habitable planet or any chemically liable planet. The idea of panspermia was defined for me by you guys differently than I thought it was, but nevertheless, I feel that we may be one of the lonely planets that had the life actually grow into what we call ourselves intelligent. Whether or not intelligent life is throughout the galaxy is another question, but life itself, whether it be microbial or otherwise, I always felt that it's prolific around the galaxy.
Okay. Well, thanks everybody. This is probably going to be our longest episode to date. It's already over an hour and 42 minutes. So let me just say quickly, if you've listened this long, thank you. I admire your patience. Or I'm sure you probably played a little Tetris or something while we were talking, but please feel free to contact us at unseenpodcast.com, or you can send an email to unseenpodcast@gmail.com. And no, James, we did not do a drinking game tonight. We should have, but I think we're getting better calibrated. Anytime Buck challenges our definition of something, we should have a drink. Then we'll be up lying on the floor on our backs and be able to talk. So anyway,
what's your definition of definition?
I shall refine the rules.
My definition of alcohol?
Every time somebody says the word creationism, we have to drink a whole glass of wine.
No,
I'll drink to that.
It would be water.
Yeah. So I've already talked about some of the stuff coming up. Episode 26 will be a meta episode where we'll talk about the previous 25 episodes and what we've done right, what we've done wrong, what we can do better, and hopefully get some input from you guys. So please send us emails to unseenpodcast@gmail.com. Tell us what you think. Or we have a subreddit for Unseen listeners. You can look that up. It's also the link to it on our homepage at unseenpodcast.com. Go to the WoW to learn more about the WoW Signal. Go to wowsignalpodcast.com. Please subscribe to this podcast if you haven't done so already. Just go to our homepage and you'll see the RSS feed, or just take your favorite podcatcher software on either your Android or iOS device and look us up on that as Unseen Podcast. We should show up because we're on iTunes and we're on lots of other things. So if you have any question about that, please feel free to email us and ask questions. This is episode 24 of the Unseen Podcast. It is, well, now it just now turned the 12th of September. It's been the 12th for Adam for quite some time. You can go to bed now, Adam. And
I'm going to go out and look at the stars.
Good for you. I've got clouds tonight, so as I usually do here in Maryland, so no chance. But you guys, we'll see you next week, episode 25. The topic is not yet determined. Let us know what you think, and we'll be back. So again, this is your host, Paul Carr. It is 12th of September 2015, episode 24. We'll see you next time. Goodbye.
Thanks, Paul.
Bye.
Bye.